Michael Öllinger из Центра исследований мышления Парменида в Мюнхене. Майкл Öllinger – один из теоретических лидеров направления исследования инсайта, и он в значительной степени сторонник одного из базовых подходов, доминирующих в этой области, теории изменения репрезентации. Сегодня лекция будет посвящена, насколько я могу судить по ее заглавию и некоторым предварительным информационным вбросам, как раз дальнейшему развитию теории и переносу ее на модели искусственного интеллекта, вычислительной модели. So, dear colleagues, allow me to introduce one of the lead specialists in the field of insight studies, Dr. Michael Öllinger. Dr. Öllinger has created several actively discussed theoretical ideas about the representational change theory, RCT. Please ask your questions through the Zoom chat. Now, I would like to give the floor to Dr. Öllinger. Michael, you are welcome, please.
Yeah, thank you very much for this kind introduction. Thank you very much for having me here to see you all back in Moscow. Yeah, today I hope you all can hear and see my presentation.
Yes.
Yeah,
sure.
Give me a thumbs up. Perfect. It should be a short introduction and overview of concepts that might be related to computational models. I will start with a very brief introduction of problem solving, then of insight problem solving. I think this is the field we are interested in. And in the third part, I will detail a little bit, but not too elaborated. It's more an overview of three different computational approaches: a connectionist model, a reinforcement learning model, and a Devinian model, so that you get a first hunch, a first overview over a very interesting and, for me, growing interesting field. Yeah, let's start with problem solving. Problem solving can be described very easily as the attempt to go from an initial state, the problem state, into a desired goal state. And there is no direct path from the initial state to the desired goal state. It is often a hindrance or an obstacle in between. And what we have to do within a problem-solving process, we have to find strategies to overcome such an obstacle. At the beginning of problem solving and of computational models of problem solving, researchers often deal with so-called well-defined problem. Why well-defined? They are well-defined because you have a very clear initial state and you have a clear goal state. And in between, there are so-called intermediate states, as you can see here in the bottom. And these intermediate states can be reached by applying certain rules. And you have to obey the following rules. You see here the very famous Tower of Hanoi problem, prototypical well-defined problem. And the rules of the problems are: you have to move only one disk at a time. Each move consists of taking the upper disk and move it. So as you can see here, there are 3 disks of different size on 3 sticks. And you have to move the 3 sticks from the left stick A to the right stick C, so that all disks rest in the same position. And there is the third rule: no larger disk may be placed on a smaller disk. And the nice thing, as you can see here, is you have a beautiful problem space. Therefore, Newell and Simon's theory is called problem space theory. It's a theory about problem solving and about search, because Newell and Simon assumed that we search via our rules and the heuristics through a problem space. And as you can see here, there's an optimal solution here at the right-hand side from the initial state to the goal state. Yeah, these are beautiful problems. And in the next slide, you see the godfathers of this approach, namely Herbert Simon. He received the Nobel Prize in economics, a very famous person, and his collaborator and I think friend, Alan Newell, and the two of them started with more or less computational models on problem solving, not on insight problem solving, but on problem solving. And as you can see here in the right picture, there's a first interpretation, a first computational model that states what entities, what processes might be necessary to formalize problems like the Tower of Hanoi problem. You see, there is a task environment, you have sensory input, you have motor actions that manipulate the environment, you have an internal representation, you have a set of prior knowledge, methods, procedural knowledge, and you have more or less this is a kind of working memory that manipulate, change, modifies the given information. And there is already, often overseen, as you can see here, this circle, a mechanism that is called change representation. And change representation is one of the main ingredients of insight problem solving. On the left-hand side, you see more or less a flow chart of an algorithm that you all might know, namely a means-ends analysis. In the means-ends analysis, it is assumed that you always take the current state and you apply rules and heuristics so that you can reach the next potential state until you reach a goal. That means you decompose the problem-solving process into sub-goals until you reach a goal. Yeah, I recommend each of you that is interested in this field to have a look at this very early work. It is very inspiring and fantastic how detailed the two of Newell and Simon thought about these things. Yeah, now let's come to insight problem solving. Insight problems are more or less also easy problems. They are not too complicated, but they are so complicated that this traditional approach that were introduced by Newell and Simon failed. Why? When we look at the definition of insight, then we can look from three different angles or from three different perspectives on the problem. First of all, and I think most of us know, the happy experience when we come up with an insight, the aha experience. The solution of such problems is most of the time sudden, unexpected, and unintended. In the task domain, we can describe insight as there are tasks that require insight. Yeah? This is a tautological structure, but most of the studies in the past rely on these assumptions. That means we have particular problems. For them, insight is more or less inbuilt, but as we have found and other groups, there is no single task that couldn't be solved exclusively, that also could solve without insight. Yeah, you can each task solve with and without insight. And there is a more process definition And this process definition means that insight occurs always when we have problems and require a representational change. And a representational change means that we either change the given problem representation, that means by grouping, chunking, and so on and so forth, we try to overcome chunks, decompose given problem elements and come up with new combinations. Or even more complicated, at the conceptual level, we have to change the goal representation and the constraints that are given for a problem. And this means constraint relaxation. We come up with new representations of the problem so that we find more flexible and new representations that help us to solve problems. And inside problem solving at the process domain is often described as a more discontinuous process. There's a lot of arguments and a lot of studies that fiddling around with this thing and whether this continues at a conscious level is the same as this continues at an unconscious level. Yeah. Good. Then, to give you an example, a very famous insight problem is the so-called 9-dot problem. As you can see here on the left-hand side, it's a very easy instruction for I would say a very difficult problem. You have this 9 given dots, and your task is you have to connect this 9 dots by 4 straight lines. And it is not allowed to lift the pen or retrace a line. This is only what you have. Yeah? This is the initial state. And now you have to play around, and after a while, a small portion of participants is able to find this, I would say, a little bit unexpected and but beautiful, symmetric move constellation. And what was assumed from the beginning, that the main source of problem difficulty is caused by drawing lines beyond the given virtual square. To overcome this boundary constraint, and so you can find the solution. These are, most of the time, we refer to Gestalt principles like fixation, grouping, or figure ground principles. Here we try to decompose the process of solving the 9-dot problem in more detail. We think we have at least 3 insights, 2 minor insights, if you would like, and 1 major insight. The first insight might be that you have to stop your problem solving attempts within the given boundaries of the 9 dots. It is only possible to maximize with your moves 8 or cancel out 8 dots, but not 9. That is, the detection of the failure of the applied strategy is for me one of the key ingredients that you can enter an impasse. An impasse, there are some speculation what might happen in an impasse. You will see computational models might help us to inform us a little bit more about these details. And what then happens, not in all problem solver, but only in a small portion, that you overcome this boundary constraint, and as a consequence, you enter a much larger problem space, namely a problem space where you can draw lines to non-dot positions. Yeah? And as you can imagine, you have an exponential growth of possibilities, and therefore a third insight might be to come up with a proper heuristic that restricts again this even larger problem space. The main insight, the main problem difficulty, of course, is to overcome the boundary constraint, but as you see, and therefore in my understanding, the 9-dot problem is a very beautiful problem for the investigation of problem solving, but it is so difficult because you have to do 3 things in a row. Good, yeah, we can differentiate between 3 stages, before an insight, before an impasse, within an impasse, and after an impasse. Then another assumption or another possibility to look at problem solving is the system 1 and system 2, a dual route approach. As you later will see, some of the models rely on this approach. Therefore, I will give you a short overview. System 1 is assumed it goes back to the work of Kahneman and Tversky, but Evans recently did a lot of work and elaborated very on these processes. Again, there is a lot of arguments. This is sometimes unclear what fast really mean or unlimited really mean. It seems that there are clear numbers behind this classification, but it's very unclear whether there is something in between automatic and deliberate and so on and so forth. That means there would be a lot of conceptual work to clarify a lot of questions in this dual route assumption. But let's take it as a heuristic that helps us to sort different kinds of processes to different systems, like in the left-hand side, a holistic or intuitive system that is unconscious, automatic, fast, unlimited, associative. And on the other side, an analytic system that we in the past always refer to human thinking as a rational logic process. It's conscious, deliberate, slow, limited, and so on and so forth. Good. These are more or less, I think, the basics that we need to enter into the realm of computational models. I think this is a fascinating field where we learn something about human thinking and play around with the notion whether machines are able to do creative problem solving and insightful problem solving. Let's begin with a few general considerations referring to Ron Sun. He's one of the pioneers in this field, and we will see later he introduced a framework called Clarion, and this is a book where he detailed and elaborate on this model. And at the beginning, why computational models? I think it's an important question for a cognitive psychologist or cognitive scientist. One argument is thinking about the necessary components, structures, entities, and operations of a model that explains human performance. I think this is cognitive psychology did this already in the past. We had our boxes, we have our processes, but at a more abstract level. Because thinking is here assumed as a mechanistic and process-oriented thing or way. And most important, there should be a rigorous mathematical model that shows you or that processes the information that has to change into the system, that comes into the system or goes with the motor actions outside of the system. What I also think is true, it provides a complementary perspective to the exclusive observation of behavior. I'm an experimental psychologist, and I love good behavioral studies. I think that's extremely important to learn about human problem solving when we look at human behavior. But of course, it would be also helpful to have some constraints or further idea what basic principles might change the information in the system or are behind these black boxes that we still have when we speak about problem solving. Yeah. And a general condition is, or precondition is that the models has to be general. It's not enough that we can explain only one single tiny effect. Yeah, when we speak about restructuring, we want a model on restructuring for different situations. And then, of course, as you will see, that's a problem. And it should be parsimonious. There are models that have a lot of assumptions, a lot of parameters, and so on and so forth. It is completely unclear what the model do. This shouldn't be the case for a good model. Good. Then another question that is, of course, important, not for computational models in general, but of course for us, we are interested what happens in an impasse, because that's the most fascinating question when we speak about insight problem solving. What happens within this impasse? Yeah. And this is so hard to investigate what happens in this impasse. Even with fMRI or EEG or other methods, we do not really see how information is restructured or integrated or varied or something else. Yeah, there are assumptions what happens from a cognitive perspective. I think most important, incubation and unconscious work plays an important role, whatever that means. Then a little more specific is the approach of Lovett and Anderson, that it has something to do with the decay of activation. Yeah, that means you have procedures that you use or knowledge that you use, and this use of knowledge increases the activation and the likelihood that you use the same knowledge or the same procedure again and again. Yeah, and when this dominant activation decreases, the probability increases that you select other information or procedures. Then another very old assumption is more from the evolutionary field. It's variation in a blind way. And more recently, there are very promising, in my view, assumptions that you have this idea of variation. And as we will see, I think this is a key ingredient. But you have also scaffolding. That means it is not only blind variation, but it is variation on the shoulders of learning. Yeah. Good. And what we have to explain is restructuring at the cognitive level, the aha experience, more or less at the phenomenological level. We want to know what is the aha experience. That means we might also need something like emotions, yeah, or motivations. Most of the models did not consider these aspects. And this all together might make an insight. Good, then let's enter connectionist models and the idea of Ron Zahn and Haley. Only to give you a first idea, there are a lot of details and mathematical things that you have to know to proper understand it. Yeah. But I think for a first approach and to tease you a little bit, I give you this slide as an overview, and more important, I show you how I try to investigate insight with this model. Yeah, the Clarion model is an acronym for a very long title, it's a connectionist learning with adaptive rule induction online. Yeah, it's hard to understand. But when we look at the detail, it's easier to understand. It is not a traditional connectionist model. Yeah, as you see here on the right-hand side, a connectionist model is most of the time you have a number of concepts, the circles here. Can you see my mouse when I move the mouse?
Yeah.
Yeah, can you
Yeah,
see
we
my
see.
mouse?
Sure.
Okay, yeah, that's important because otherwise I speak about things and you have no idea what I mean. That means the circles can be concepts, hypotheses, and the connection between the circles has something to do. It's a rule or at least a connection between two concepts. Yeah? This is the traditional connectionist approach. But additionally, the system has also an associative approach. Yeah? It's called implicit learning. This is the system one that I introduced before. Yeah? The holistic, the automatic, the unconscious, the fast, and so on. And this is the system two, the conscious, the deliberate, the slow system with hard constraints. Yeah, and the implicit model relies on an attractor-based model. That means you have a number of neurons that are grouped in a way, and they are trained by incoming data. And what the model do, and I think this is something interesting, they assume that each information that comes into the system goes in parallel in the explicit, but also in the implicit system. That means you have a more freely associative activation and a more clearer, more detailed, more rigid information. Yeah, this is the basic idea. Importantly, you see here, it's the stochastic distribution. It's a so-called Boltzmann distribution, often used, the Boltzmann machine in machine learning or in connectionistic models. For us, it is important there is the parameter alpha, and this parameter is in the physical sense temperature. In the information theoretical sense, we can speak about noise. And as you will see, noise might play a role for variation. So let's come to the second part of the connectionistic model, namely how did they investigate the model. And they used a very interesting problem, introduced by Durso and colleagues. And what Durso and colleagues were interested there, what are the underlying semantic networks that are established and differentiate solvers from non-solvers that solved a difficult problem, an insight problem. And they used a very, I think a funny problem. A man walks into a bar and asks for a glass of water. The bartender points a shotgun at the man. The man says, "Thank you," and walks out. And you can test yourself when you are new to this problem. Maybe you start up with a representation of the problem that has something to do with a bar scene. Yeah? The solution to the problem is more, I would say, unusual. The person suffers from an hiccups. This means, yeah. And what the bartender did is, by pointing the gun on the person is surprised, and the surprise remedies the hiccups. That means the insight here is to overcome the original activation of a bar scene where a person is thirsty and wants a glass of water, and restructure it in a way that it has something to do with hiccups. Yeah, the idea clear? And now let's have a look at the procedure. That's important here. The procedure is I have to put your pictures away. Oh, that's better. The persons the participants in the experiment were allowed to ask yes/no questions to the experimenter, yeah, until they found the solution or the upper time limit was reached. After that, the experimenter separated the persons in solvers and non-solvers. And then in a second phase, they provide 40 concepts that either has to do with the original bar scene or has to do with the hiccups sequence. Yeah. From these 14 concepts, you have 91 randomized pairs, and this randomized pairs means they always get a pair of two concepts and have to estimate how close these are related. From this information, they set up these graphs. Here for the solvers, you see one of the key concepts of the solvers, the semantic knowledge of the solvers was, one key concept is relived, connected to remedy, and remedy is connected to surprise, and surprise is activated by shotgun. Yeah? When you look, I don't know whether you also see the pictures always from you. I think you have to, because I share my screen. In the bottom, you see the non-solvers graph, and here the concept of bartender is very strongly activated and connected to the other concepts. And there is no connection between surprise and remedy. Yeah. Good. So then let's come again to the Clarion model. What they did is they took the non-solvers graph as initial knowledge base for the model. They feed in the knowledge graph of non-solvers into the system, and the system now played around with this knowledge graph. And this is an iterative process where the system more or less asks questions to the experimenter, as we've seen before. And until an internal confidence level isn't reached, the system again and again go in this iteration and change the knowledge structures, and always select, according to the Boltzmann distribution, the most promising candidate for the next question. And after a while, at least some of the systems were able to find a graph that is similar to the solvers graph. And as you can see here, an important thing was that when you increase the noise level, you see here on the x-axis, the number of the voice level, the noise level, and on the y-axis, the number of edges that differing from the solvers graph. Yeah? And after increasing the noise, you have a good match between the generated graphs and the solvers graph. It was not perfect. I think that's important. And you see there's a kind of plateau. It does not matter to increase the noise level further than, I would say, 10. Yeah. After that, there was no increase in the quality of the matching process. But it gave us the first hint that noise and variation might play an important role. Good.
Michael,
yes?
I'm sorry, I have to interrupt you. 3 minutes left.
3 minutes, yeah, I see it on my clock.
Okay.
Then I skip the reinforcement learning part and kick into the Darwinian part as the last part. The Darwinian idea is that we have a Darwinian process that relies on copying representations. And what the model is doing, each of this representation, here you have, for example, a small network of 3 activations. You copy this with a small deviation, and this small deviation is copied again and again until a solution is reached or a major transition within the representation appears. That means this copying process, this replication process, might help us to feed in variation in the system so that something new can happen. We used a very famous insight problem, the so-called 4-tree problem. And the question is, a landscape gardener is given instructions to plant 4 special trees so that each one is exactly the same distance from each other. How is he able to do? And most people, why is this problem an insight problem? Because most people start with the misconception that the solution has to be in a 2D representation. Yeah? And as you see at one glance, the diagonal is of course longer than the length of the sides. This is wrong. You have to overcome this misconception by coming up with a 3D representation where you have 3 trees in the plant and 1 in the height as a tetrahedron solution. And that means you have to overcome a 2D constraint and finding a 3D solution. Yeah, our model relies on two modes of thinking. On the one hand side, you have a Bayesian approach. That means you have information that can be updated, that can be selected, and so on and so forth. On the other hand, you have an evolutionary model that should be activated when the Bayesian model gets stuck in an impasse. We also used attractor-based models that, as you can see here as an example, you have a number of representations that compete against each other, and the best representation according to the fitness landscape. And the fitness landscape is determined, of course, by the affordances of the solution. And the affordances of the solution is, first of all, the solution has to be in the 3D space, and second, the lengths have to be equal distance. Okay, yeah, what we found was, and this is almost the end of my talk, what we found was that models that showed less repetition, yeah, that earlier switched from the Bayesian approach into the evolutionary approach, were more successful to find the solution. We also published this results, and we try to continue with the model. And this is my last slide to wrap up a little bit what I said. First of all, insight problems might be a particular class of problems which require the interplay of prior knowledge and restructuring. And this is, of course, a challenge for the standard models within reinforcement learning or the older models on computational models on problem solving. It seems that variation and recombination might be a key ingredient for solving an insight problem. That means also this can give us a hunch what might be important within an impasse. Yeah? And there are different computational approaches that are able to simulate certain facets of insight problem solving. This is on the one hand side, it's a nice finding. On the other hand, it's a little bit weird, because I would assume that the brain might have a single or a particular computational principle to come up with a solution. And then At the end, computational models help to clarify potential cognitive mechanisms and inform further theory building and empirical research. Yeah, I feel inspired by these models. For me, it is a future interest to learn more about these models, to play around with these models, but of course, to continue with basic research on behavior and experimental work on insight problem solving. There's a lot to do. Thank you very much for your patience.
Michael, thank you for your interesting and informative talk. Colleague, we have time for one short question.
Oh.
So we have a question in our chat. Michael, could you provide full citations to your presentation?
Full citations?
Yes.
Yeah, you mean for the literature?
I think yes.
Yeah.
Yeah, sure. I can also provide the presentation that you have more time to go through it if you want. I can send it to Vladimir as a PDF.
Thank you.
Thank you very much.
You're welcome.
It would be possible to put it on the website as well.
Yeah, and of course you are welcome. If there might be questions, please do not hesitate to send me an email or a message. I hope we can continue our discussions and our work together in the future.
Okay.
Oh, great.
All right. Thank you,
Michael.
Michael.
We have time for one question.
Good.
I have a short question. What do you think, Michael? Is it possible to make a universal model which be able to solve all the kinds of insight problems, or do we need to model very different models which based on different ideas?
Yeah, that's a very good question. I would say Ron Sun would claim he has this model with the Clarion model. Yeah, and he has also a model that incorporates motivational aspect, emotional aspect, and he shows decision making and so on and so forth. Yeah, it's a very broad model. I would recommend to have a look at this, at least to scan through it. But I'm not so sure whether it has really physiological and neuroscientific plausibility. Yeah, I think we have to separate models that can do things like humans or do it in the same way like humans would do it. I like this evolutionary approach. I can assume that, or I would assume that the brain has some kind of neural Darwinism in it. And I also like the reinforcement learning stuff that now showed from different perspectives that the combination with reinforcement learning might be something that could be linked to the dopamine system in the brain and so on. There are some extremely exciting and promising tendencies right now. And I hope maybe next year we can continue this chat and this talk, and I have a better answer to your question.
Thank you.
Okay, thank you. Michael, thank you a lot for your talk. So we can finish our first lecture, and I hope our common work will be continued. Thank you very much.
Thank you very much for the invitation, and have a good time at your conference. Yeah, it was a great pleasure and a great honor to be here. Have a good
Thank you,
time.
Michael, for a great presentation.
Okay.
Thank you.
Yeah.
Bye.
So, okay, thank you, Michael. I will check that it recorded successfully, and I'll let you know once the recording is up on the YouTube.
Yeah, thank you.
Okay.
I'm looking for. Good. So then, thank you very much for your help, and have a good time.
Okay. Well, yeah. Thanks for coming virtually.
Oh, I have. I make you again to the host.